Hello to all. In the following video, I will explain what does it mean to have a signed number. Okay, when we say signed number, we mean that the number is, in this case, is negative. Okay, the idea of a signed number is that when we put signed decimal, yeah, the number can be a negative number. And how a negative number is represented? Because eventually, if we consider it as a binary word, yeah, 8 bits, how do we interpret, we represent, yeah, we understand or we read that number as a negative number? So the idea behind it is to consider that one of the bits in the binary word, yeah, in the 8 bits here, is not, it doesn't really represent it's not really part of the complete number. It becomes a bit that represents if it's a negative or a positive number. And how do we do that? Eventually, in the computer science standards, what was decided is that the last of the bits, the biggest one, number, the 8th bit, in case of using signed numbers, yeah, it will be it will represent the negative. It will represent or will show that the number is a negative number. So if we now, as you can see, if we are in binary form, it really doesn't matter because eventually we will see it as a binary representation. But if we want to show it as a decimal, as a number, if we have a number, if a number 1 here, it will represent the number here as negative if we consider it as a signed number representation. Let's show it with an example. If to AL I move the following number in binary form: 0, 0, 0, 0, 0, 1, 1, 0, 1, 0. This is the representation of number 10. Okay, if we execute it, we'll have number. Okay, 1 second. Sorry, I forgot to put the B. Never forget to put the B because it wouldn't know that it will think that it's really a representation of the number 100, 101. Okay, then now we have that representation, okay, in binary form, which is really number 10, and in signed decimal it's number 10 too, because in both cases it is a positive number. Okay, now if I decide to put a 1 here, okay, in that moment we'll have two different representations of the number. In case it is unsigned, we'll see a big number. Probably think of now it's 2 by 0, 1, 2, 3, 4, 5, 6, 7. 2 by 7, which is 128, plus 10, 138. It should be something like that. Yeah. So let's try it. If we execute 138, as I mentioned before, that's a representation of the binary in unsigned decimal. But if we put it as a signed decimal, the number will be, well, in this case, it's negative 180. But still, I mean, wait a second. Why do I have negative 118 when eventually what I should have had here is no less than the negative 10? Eventually, what I said before, if we put a 1 in the end and we represent it as a signed decimal, we should have had the representation of negative 10 in the register. So the real reason why it's not showing 110, negative 10, is because when we turn it around, when the number becomes negative, the negative, what the numbers, the ones it goes to the maximum negative number, which means zero. When we put all numbers at 0, what we'll see is a negative 128 instead of negative 0. Okay, we can even try it, and from that point on, each time we add a number, yes, as you can see, that's the maximum or the minimum number possible. While if we put it as a sign decimal, it is 128. It's perfect because it's symmetrical. So from now on, each time we add a number in these 7 bits, it will just sum. Okay, it will sum that number. If we put a 1 here, yes, it will be it will just sum it will be minus 128 plus 1. If we put here, I don't know, that's 2 by 0 by 1 by 2 by 3. If we put here a 1, it will be 120 because it's 2 powered by 3, okay, plus minus 128, which it's 128 plus 8, yes, and so on. So when it becomes negative, the values that we add with the bits on bits, it starts adding themselves to the value of the number, and it reduces its negative number and put us closer to the number 0. That is why it's not symmetrical. If I put 1 0 1 0 here, it's not negative 10, it's just minus 118 because it's 128, it's minus 128 plus 10. Okay, and that is how we represent negative and positive numbers. So if I decide now to make a shift to the left, let's remember that shifting, a shift to the right, for example, let's remember that shifting to the right will divide the number in 2. It should show us the number 69 if we divide it by 2. Shift right, AL 1. I execute, and I have plus 69. Now this is a small problem because it shouldn't have shown us plus 69. There is a reason, by the way, and it is because the value in the left, yes, when we shifted the number, let's try it again. First we put the value, again, sorry, 10001010. Okay, now if we shift to the right, it shifted, but it puts zeros at the left side. Okay, if we don't want that to happen, yes, we have to tell him that we carry a 1 instead of a 0. Question is, if we do that, and we start again, so what we have is that because in the other side by default it has zeros, if we want to maintain the number as negative, we have to afterwards either we sum a number at the end. For example, we can put like add to AL the number 10000000, for example, in binary form. See, 1 2 3 4 5 6 7 8. Okay, so in this way we can ensure that it maintains its negative form sign. So we start by executing that, we divide it by 2, and we add this. But the only problem with it is that it's really not showing. It's not showing the right representation of the number, because now it's truly what it's doing is that showing the 128 plus negative 128 plus 69, and that is 59. Okay, so it should have shown us 69. In the following video, I will explain how we can improve this, yes, and make a right representation of the number.